Hello everyone, and welcome to this second block of the CU intensive course. This is the first episode of the second block of theory lessons. If you remember from yesterday, we mentioned that this theory lesson is going to be dedicated to remote sensing. So we're going to start with a brief introduction. Then we are going to see the principles of optical oceanography and ocean color remote sensing. We will see the classification schemes of water types. Then we're going to see which data processing levels can we access for remote sensing data. We're going to have an overview of the main ocean color sensors, and we will finish with some remote sensing techniques for monitoring hubs. In this first episode, we will start with an introduction to remote sensing. As you probably know by now from the first block of theory lessons, it is very, very important to forecast, monitor, or detect hubs in order to prevent environmental, human, or economical impacts. Hubs can be monitored using either in situ methods or remote sensing techniques. Remote sensing techniques can be done with drones, aircrafts, or satellites. Obviously, we are going to focus on satellites. But just for you to know, drone-based hubs monitoring is an emerging remote sensing technology that can provide users with on-demand, high spatial and temporal resolution images at low cost. So it has a lot of potential. The problem with drones is that there are still not standard processing methods to process the images for hub studies. So it has a lot of potential, but it's still an emerging technology. Satellite remote sensing allows collecting data frequently and over a large area, including regions that are difficult to access. So this is an advantage with respect to in situ methods. However, satellite remote sensing has many limitations and will never be able to replace in situ data. The first limitation is that most of the signal comes from the first top few meters of the water column, and the depth of this layer depends on the water clarity. And the water clarity is related to the concentrations of chlorophyll and other suspended matters that we can find in the water. For example, on the bottom right-hand side panel, we can see that the water is very, very clear. So in this case, the satellite will be able to see the first maybe 20, 30 meters of the water column. However, in very turbid waters, like the image on the left-hand side, we can see that this turbidity makes the water very dark, so the satellite cannot see very much, maybe maximum 10 meters or sometimes even less. That means that the chlorophyll concentrations measured by satellite remote sensing will be underrepresenting the values that we find in deeper layers. For example, if we see this chlorophyll profile here on the right-hand side, we see that on the first few meters of the water column, the chlorophyll concentrations are low. However, we find a chlorophyll maximum at a depth which is approximately 40 meters, more or less. If we look at the penetration depth of the satellite, we see that the penetration depth, which is approximately 20% of the euphotic depth, that means the depth of the water column where the sunlight reaches, okay? So in this case, we see that the penetration depth is less than 20 meters. That means that the chlorophyll is only measured in this first less than 20 meters of the water column. However, we are missing this deep chlorophyll maximum. We cannot see it with the satellite. This can also be observed in this map here. This is a map of MODIS Aqua Chlorophyll A productivity in the North Atlantic Ocean, and we can see that according to the satellite image, most of the central North Atlantic is, it doesn't have any chlorophyll concentration. If we see the color scale here, we see that the values are approximately 0. So there is no chlorophyll. However, if we do a profile, not a profile, we do a section from the southern hemisphere crossing the middle of the Atlantic up to 40 degrees north, we can see that in regions where the chlorophyll concentration is 0 at the surface, we find chlorophyll maximums at deeper layers, approximately around 100 meters depth. And this cannot be seen with a satellite. Moreover, satellite measurements do not capture non-uniform vertical distributions of phytoplankton. That means that in situ data or knowledge about the local species might be necessary in order to interpret the data correctly. From a remote sensing image, we might have a misunderstanding of the region, so we really need to know what we are looking for. This structure, vertical structure of the phytoplankton can be seen in these images here, in these graphics. We can see, for example, picophytoplankton has the maximum concentrations in depths approximately 20 meters, something like that. So this could more or less be seen by the satellite. However, if we look at the nanoplankton, we see that the maximum concentrations are in depths higher than 100 meters. And this while at the surface, the concentration is roughly 0 or very close to 0. So these values will not be taken by the satellite, will not be measured by the satellite. And the same happens, for example, in this microplankton graphic, where we can see that the concentration is 0 almost everywhere, including at surface, while we can find some maximums at higher depths. And this, again, cannot be seen by the satellite. However, remote sensing data is very useful and can be used to inform decision makers. For example, we can inform where to collect water samples for in situ analysis, which toxins need to be measured, whether drinking water intakes need to be changed or moved, or whether a fishery needs to be closed. So it is a very useful tool, but a thorough study should always involve both the analysis of satellite images with in situ data. And when we talk about in situ data, we need to include field measurements, that means water samples, to sample, for example, toxins. But we also need meteorological data. If you remember, certain hubs require low wind conditions, slow-moving water, warmer temperatures, so we also need meteorological data. As I was saying, if we talk about field data, we might need to measure nutrients to see if we are under an eutrophication problems. We need to count the cells to see if it is really a hub or it's a normal bloom. We might have to identify the species, and of course we will have to look for toxins. And meteorological data, as I said, we need to measure water temperature, air temperature, wind speed, rainfall. Remember that rainfall can wash off any pollutants and bring them to the watercourses. Are you ready to learn the basic principles of optical oceanography and ocean color remote sensing? If so, please join me in the next episode.